Hello everyone. Before we dive into today's topic, we want to take a moment to thank you for your support. Every like, comment, and subscription truly makes a difference and helps this channel grow. If you enjoy our content and don't want to miss the next videos, subscribe to the channel and activate the bell to receive all notifications. In the frozen depths of the solar system, where sunlight is barely a whisper and the cosmic night shrouds everything in perfect silence, a blue planet harbors a secret that defies astrophysical logic. Uranus, an ice giant cloaked in ethereal hues, emits more heat than it receives. This seemingly technical detail hides a far more unsettling truth. Something at the heart of this distant world refuses to stop burning. For decades, Uranus was considered the most mysterious and lethargic of the giant planets. Unlike Jupiter, Saturn, and Neptune, known for their intense atmospheric activity and complex internal dynamics, Uranus appeared as a sleeping sphere, immersed in a millennial torpor. When the Voyager 2 probe flew by in 1986, it returned the image of a surprisingly tranquil planet. No massive cyclones, no evolving storms, just a uniform, almost ghostly calm. But beneath that seemingly motionless surface, something was simmering. Voyager's instruments detected thermal emissions that didn't match the models of the time. Uranus appeared to emit only an infinitesimal amount of internal heat, as if it had exhausted all residual energy from its formation. And yet today, thanks to new ground-based observations and astrophysical simulations, we learn that reading was partial, perhaps even misleading. The University of Houston, in collaboration with observatories in Chile and Hawaii, has revealed a fascinating anomaly. Uranus radiates about 12.5% more energy than it receives from the Sun. This excess energy, invisible to the eye but detectable with infrared instruments, signals the presence of an active internal heat source. Heat that, nearly 3 billion kilometers from the Sun, should not exist. Where does this energy come from? Scientists hypothesize that Uranus is slowly releasing the residual heat of its formation, a process theorized but never so clearly observed in such a distant planet. According to current models, when planets form, the immense gravitational energy from the collapse of primordial material is converted into heat. In giants like Jupiter and Saturn, this heat radiates conspicuously. In Uranus, it appeared to have been frozen. Now we know that's not the case. The implications are profound. For years, Uranus was thought to be thermally dead, incapable of sustaining internal convection, and therefore devoid of complex geological or atmospheric dynamics. But the release of heat suggests a more active internal structure than expected, with possible convective currents slowly moving layers of water, ammonia, and methane beneath its surface. This internal activity might also explain another mystery: the planet's strange tilt. Uranus rotates virtually on its side, with an axial tilt exceeding 80 degrees. According to a fascinating hypothesis, a massive collision with an Earth-sized object, billions of years ago, not only tilted the planet but also trapped heat within it, locking it under a crust of convectively stable layers. Today, that heat may finally be making its way to the surface. And it doesn't stop there. The energy release could also affect Uranus's moon system. Its 27 known moons orbit in strange, often retrograde and misaligned paths relative to the planetary equator. Among them, Miranda is the most enigmatic. A relatively small moon, yet its surface is scarred by deep canyons and fractures that seem carved by internal forces. Could Uranus's internal heat have influenced its most haunting moon, fueling a long-lost geological activity that remains partially understood? The clues are abundant. Recent models suggest that Miranda could host a subsurface liquid ocean, maintained in a fluid state by tidal heating caused by Uranus. If confirmed, we'd be looking at a potential astrobiological niche, far from the Sun yet rich in energy. A possibility that could upend our notions of life in the solar system. Meanwhile, unexpected climatic variations are observed on the planet's surface. Seasons on Uranus last more than 20 Earth years, and telescopes have documented sudden storms, changes in brightness, and shifts in cloud composition. It's possible that internal energy is directly influencing the atmosphere, awakening a world we thought dormant. At the same time, the scientific community is increasingly calling for a new mission to Uranus. Voyager's data is now nearly 40 years old, and modern instruments could unveil unimaginable details. An orbiter equipped with spectrometers, penetrating radars, and thermal detectors could explore the planet's internal composition, map its winds at various depths, and analyze the interaction between its magnetic field and atmosphere. But the stakes are even higher. Uranus is not merely an exotic, forgotten planet on the outskirts of the solar system. It's a key to understanding hundreds of similar planets already discovered around other stars, the so-called sub-Neptunes, or ice giants. Bodies between 2 and 4 Earth radii that represent the most common class of planets in our galaxy. And yet, ironically, we've never studied even one up close. The new window opening with the mystery of Uranian heat compels us to look again in that direction. Because perhaps, in that silent corner of the sky, lies the answer to a far greater cosmic question. How do ice giants really work? And what secrets might they still hold? If Uranus truly is a living laboratory of what happens in the ice worlds scattered across the galaxy, then unveiling its every detail becomes essential. One of the first questions raised concerns the distribution and origin of this heat. It's not just leftover thermal residue from the planet's early days. Scientists speculate that Uranus's particular composition plays a key role in its ability to retain energy. Alternating layers of water ice, ammonia, and methane, compounds known for their unique melting points and thermal conductivities, may form a kind of cap that traps heat like a blanket, slowing its release to the exterior. This thermal behavior is even more intriguing when compared to Neptune, its twin in mass and composition but far more dynamic. Neptune emits twice the energy it receives from the Sun and displays significantly more atmospheric activity. Why has Uranus remained so silent for so long? Some theories suggest that the catastrophic collision that tilted it also scrambled its internal layers, radically altering the convective transport of heat. Others propose that its atmosphere is simply more opaque, masking underlying processes. But the new thermal detections suggest that something has finally reawakened. Perhaps the heat has remained encapsulated for billions of years and is only now, for reasons still unknown, managing to slowly escape. One of the most fascinating scenarios envisions Uranus entering a phase of climatic reignition, a process in which the thermal balance gradually shifts, altering the equilibrium between interior layers and the atmosphere. Some models even hypothesize that millennial climate cycles might occur, similar to Earth's ice ages but on a planetary scale and with alien rhythms. This would mean that Uranus, once thought static, could periodically enter phases of heightened activity, with potentially vast impacts on the entire planetary system. This also brings its magnetic field into the equation, one of the most bizarre in the solar system. Far from being centered and symmetrical, Uranus's magnetic field is tilted more than 50 degrees from its axis of rotation and appears to originate from a non-central region of its core. This makes it unstable and mutable, prone to unpredictable variations. If internal heat is increasing, it could trigger further changes in the magnetic field, affecting the magnetosphere, auroras, and possibly even the atmospheric distribution of gases. In other words, Uranus may prove far more interesting than we ever imagined. Even from an observational standpoint, the future promises exciting developments. The James Webb Space Telescope has already begun collecting high-resolution data on Uranus and its moons. Infrared observations have revealed banded thermal structures in the upper atmosphere and a far more complex seasonal behavior than expected. Alongside new radio astronomy tools and three-dimensional climate models, we're laying the groundwork for a revolution in our understanding of this bluish giant. Meanwhile, an entire generation of scientists is advocating for a dedicated mission, an orbiter and atmospheric probe capable of precisely mapping the planet over several years. The goal is ambitious: to penetrate below the clouds, analyze the deep composition, measure the thermal gradient, monitor the magnetic field in real time, and perhaps even attempt a controlled landing on one of the major moons. A mission akin to Galileo at Jupiter or Cassini at Saturn, but with the chance to discover something entirely new. A world we have looked at, but never truly seen. Why does this matter? Because Uranus, so distant and seemingly secondary, represents a bridge to a class of planets abundant in the galaxy. The so-called ice giants are everywhere, yet we know none of them up close. Every discovery on Uranus is a window into hundreds, perhaps thousands, of worlds out there. Some may harbor internally heated moons, subsurface oceans, or chemical conditions capable of sustaining exotic life forms. If Miranda or Ariel, for example, do indeed hide oceans beneath their ice, we could be facing ecosystems never before imagined. In this context, Uranus's mysterious internal heat is not just a thermodynamic enigma. It's a powerful narrative key, a scientific and emotional hook to place a forgotten world back at the center of the debate. It represents the cosmos's ability to surprise us, even when we believe we've already categorized everything, even when we deceive ourselves into thinking a planet's silence means the absence of life or history. The truth, as so often in deep space, is much more complex and much more fascinating. Uranus is calling to us from afar, not with roaring storms or radio bursts, but with a thermal whisper that compels us to reconsider what we think we know. It's time to listen.